Maybe you can share more videos today if possible.
When you keep a dipole inside a uniform external electric field, the charges experience equal and opposite force, and so the dipole as a whole experiences a net zero force. But the two forces makes the dipole turn. In this case, it will tend to turn it this way, and as a result, there will be a torque acting on it. And what does that torque do? Well, it will always try to align the dipole in the direction of the field. Let me show you. If you have the field to the left, and let's say you keep a dipole this way, the torque will act in a way to try and align it. And once it's aligned, the torque disappears. It doesn't matter how the field is, the torque will always try to align the dipole in the direction of the field. And this is something we've seen before in the previous videos. And so if you need a refresher, feel free to go back and watch our video on intro to torque acting on dipoles. But what we're going to do in this video is figure out how much that torque is in terms of the dipole moment and the electric field. So let's do that. So how do we calculate torque in general? Well, if there are two equal and opposite forces acting on any object, we call that as a couple, then the torque due to that couple always equals strength of the force. The forces are equal, so strength of the force multiplied by the perpendicular distance between them, which I'm calling as L. And over here, L would be this distance. This is the perpendicular distance, right? This is our L. So now we need to find what this force is and what this length is in terms of what? In terms of the electric field strength, in terms of the charge, and the length of the dipole. So let's put all of that. So let's say the charge is Q, and the length of the dipole is, I don't know, let's call it as D. Sometimes in textbooks we call it as 2A. It doesn't matter, you can take any variable you want. So let's see, can I calculate what the force is? Well, yeah, I know the charge, I know the electric field, and from that I can figure out what the force is. And similarly, I know this length is D, that's the length of a dipole. And if I know this angle, and you can assume that angle to be, say, theta, then from trigonometry you can figure out what the length is. Ooh, so we can simplify, and I want you to pause the video and see if you can simplify this yourself. You have everything that you need. So pause and give it a shot. Don't worry about going wrong, it's fine, but always try to first do things yourself. All right. So let's start by figuring out the force. How much is the force? Well, for that, I look at the electric field. What is it? Remember what's the meaning of electric field? It represents the force acting on 1 coulomb. So if I keep 1 coulomb, the force is E. If I keep 2 coulombs, the force is 2E. So if I keep Q coulombs, the force would be Q times E. So from the definition of the electric field strength, I know the force is going to be Q times E. So that's our force. Okay, now how do I figure out this length? Well, for that, let's take this angle to be theta. This is the angle between the dipole moment vector and the electric field vector. And now from this right angle triangle, I know the hypotenuse. I want to figure out what the opposite side is, and so I can use sine theta. So sine theta is going to be L divided by D. So L equals D sine theta. Yay, we found that as well. So let's write that. This is going to be D times sine theta. Okay, can we simplify this even further? Oh, yes, we can. I see something. I see something. Do you see it as well? Q times D. We've seen that before. What do you call the product of the charge and the length of the dipole, or the distance between the two charges? Hey, that's our dipole moment. Remember, that represents the strength of our dipole, and we call it P. So 2 times D is P, and we have E, and so we get P times E times sine theta. And I think we're done. We're actually almost done, not completely, because this represents the magnitude of the torque. But remember, torque is a vector quantity. It has a direction as well, which means we should be able to write this as a vector equation. But how do we do that? Well, I look at the right-hand side and I say, look, I have 2 vectors. P is the dipole moment, which is given by this vector, from negative charge to positive charge. That's a vector. And E is the electric field vector. So I have 2 vectors being multiplied. So that means we're talking about vector multiplication. And then we have cross products and dot products. And sine theta comes under cross product. That's the vector product. So what I'm trying to say is that we can now write that the torque vector, we can now write it as P cross E. P cross E. Because the magnitude of P cross E is P sine theta.
Continuous charge distribution. We know that electric charge is quantized. The smallest quanta of charge can exist as either positive E, which is the charge on a proton, or negative E, which is the charge on an electron. So, a charged body basically consists of many discrete charges with magnitude E. To determine the electric field at a point due to a charged body, it would be impractical to work in terms of discrete charges present at the microscopic level. For example, even 1 microcoulomb of charge will contain over 10 to the power 13 quanta of charge. In such situations, we divide the charged body into small elements. Next, we find the electric field generated by these individual elements at the given point, and then add them to find the net electric field. There are 3 types of continuous charge distribution: linear charge distribution, surface charge distribution, and volume charge distribution. In a linear charge distribution, the charges are distributed along a line. An example of such a distribution is a uniformly charged metal wire. In a linear charge distribution, we consider a small line element of length delta L, containing the charge delta Q. The linear charge density, lambda in this case, is defined as charge per unit length. The unit of linear charge density is coulomb per meter. The second type of charge distribution is where the charges are distributed over an area. Such a charge distribution is called surface charge distribution. An example of such a distribution is that of a charge sheet. To calculate surface charge distribution, we first divide the area into small equal surface elements, delta S. The charge contained in each surface element is denoted by delta Q. Then the surface charge density, sigma, can be defined as the charge per unit area. The unit of surface charge density is coulomb per meter square. The third type of charge distribution is the volume charge distribution. In such a type of charge distribution, the charges are distributed over a volume like that of a sphere or a cube. For a volume charge distribution like that of a charged solid body, we consider small equal volume elements, delta V. The charge contained in each volume element is denoted by delta Q. The volume charge density, ρ, is defined as the charge per unit volume. The unit of volume charge density is coulomb per meter cube. Now, let's find the electric field due to a linear charge distribution. Here, we have to find the electric field generated by a wire at a point P. The wire is divided into small equal line elements, each of length delta L. The first element of the wire is at a distance Ri from the point P. The electric field due to the first element at point P is given by Coulomb's law. Here, Ri cap is the unit vector in the direction from the first line charge element to the point P. We can find out the electric charge in the element of length delta L by using the concept of linear charge density. The charge delta Q contained in the element delta L is given by the product of linear charge density, lambda, and the length of the element delta L. So now, let's substitute the value of the charge to find the electric field at point P due to the first line charge element of the wire. Similarly, we find the electric field at point P due to the other line charge elements of the wire. Now, to find the total electric field due to the wire at point P, all we have to do is to add the electric fields due to each element. Since the number of charge elements is very large, we practically integrate the electric fields instead of adding them. However, for the sake of simplicity, we will stick to addition here. Note that while adding the electric fields, the horizontal components of the electric field generated by the elements get cancelled out, whereas the vertical components get added. So, the net electric field due to the wire at point P is along the direction normal to the wire. So, using Coulomb's law, the superposition principle, and the concept of charge density, we can find the electric field for any type of charge distribution. Let's recapitulate the key points covered in this animation through this concept map.
वीडियो में हम समझेंगे इलेक्ट्रिक फ्लक्स और गॉसेस लॉ के बारे में। गॉसेस लॉ को समझने
Hello, Dan here from howtomechatronics.com. In this video, we will learn about electric flux and Gauss's law. In order to understand Gauss's law, first we need to understand the term electric flux. Electric flux is the rate of flow of electric field through a given surface. It is the amount of electric field penetrating a surface, and that surface can be open or closed. First, we will take a look at an example of electric flux through an open surface. These red lines represent a uniform electric field. We will bring in that field a rectangle, which is an open area, and we will divide the area into very small elements, each with size dA. dA is called the differential of area. Now we are going to make the area dA a vector, with a magnitude dA. The vector direction is always perpendicular to the small element dA. The electric flux that passes through this small area, d phi, also called a differential of flux, is defined as a dot product of the magnitude of the electric field E and the magnitude of the vector area dA times the angle between these two vectors theta. The total flux is going to be the integral of d phi, or the integral over the entire area of E dot dA. It is a scalar quantity, and the end result can be positive or negative. If the flux is going from the inside to the outside, we can call that a positive flux, and if it's going from the outside to the inside, that's a negative flux. The unit of electric flux is Newton meters squared per coulomb. To get a better understanding of what electric flux is, I will bring into this electric field three rectangles. In fact, these rectangles represent one rectangle with different orientations. Now let's explain the flux through each one of those open areas. In the first case, the area is perpendicular to the electric field, and the angle between their vectors theta is 0. Cosine of 0 is 1, so the electric flux is going to be E times dA. Here we have the maximum flux. In the second case, the angle between E and dA, theta, is 60 degrees, and cosine of 60 degrees is 0.5, so the electric flux will be half of E times dA. In the third case, the area is parallel to the electric field, which means that their vectors are perpendicular to each other, and the angle theta between them is 90 degrees. Cosine of 90 degrees is 0, so the electric flux here will be 0. This means that nothing goes through this rectangle, so the flux is 0. Now let's take a look at a surface that is completely closed. How do we define flux? Here we can put some normals, dAs, in different directions. By convention, the normal to the closed surface always points from the inside to the outside. Now we can calculate the total flux going through this closed surface. The total flux is equal to the integral of d phi over the entire surface, which we write as the integral over the closed surface of E dot dA. The total flux can be positive, negative, or equal to 0. If the same amount of flux is entering and leaving the surface, we have 0 total flux. If more flux is leaving than entering the surface, then the total flux is positive. Opposite, if more flux is entering than leaving the surface, we have negative total flux. Let's take a look at another example and see how the electric flux is related to Gauss's law. We have a point charge plus q in the center of a sphere with radius r. Now we will take a small segment dA, which vector is perpendicular to the surface and is radially outward. The electric field generated by q at this point is also radially outward. This means that dA and E anywhere on the surface of this sphere are parallel to each other, and the angle between them, theta, is 0, and cosine of 0 is 1. The differential of flux through the small surface area, d phi, is equal to E dA. The total flux phi is going to be the integral of d phi, which is the integral over the closed surface E dA. The magnitude of the electric field everywhere is the same because the distance from the charge is the same at each point. So we can pull that out of the integral and we are left with E times A. The total area of the sphere is 4 pi r squared, and the total flux through this closed surface is simply E times 4 pi r squared. From the previous videos, we know that E is equal to K times Q divided by r squared, which is equal to Q divided by 4 pi epsilon naught r squared. Here we can cancel out 4 pi r squared and we can notice that the total flux is equal to Q divided by epsilon naught, where epsilon naught is the permittivity of free space. The flux doesn't depend on the distance r. We would get the same result no matter the size of the closed surface around the point charge. What if we bring more charges inside the closed surface? The equation should also hold for any system of charges inside. This leads us to the Gauss's law, which says that the electric flux going through a closed surface is the sum of all charges q inside the closed surface divided by permittivity of free space epsilon naught. If the flux is 0, that means there is no net charge inside the shape. There could be positive and negative charges inside the shape, but the net is 0. No matter how weird the shape, Gauss's law always holds, as long as there is a perfect symmetry in the charge distribution inside the surface. So, in order to calculate the electric field, you need a symmetry, and there are three types of symmetry: spherical, cylindrical, and planar symmetry. We will start with the spherical symmetry. This is a thin hollow sphere with radius r, and we will bring a positive charge q into the thin shell, which is uniformly distributed. Now we need to find the electric field inside the sphere at a distance r1 from the center and outside the sphere at a distance r2 from the center. To do that, we need to determine our Gaussian surface. In this case, we will choose concentric spheres as Gaussian surfaces, one smaller with radius r1 and other larger with radius r2. Now we need to use two symmetry arguments that will help us calculate the electric field. The first symmetry argument shows that the magnitude of the electric field is the same at any point, since the charge here is uniformly distributed. The second symmetry argument shows that if there is an electric field, it must point either radially outwards or radially inwards. In this example, we have a positive charge, which means that the field is pointing outwards. From the previous equations, we know that the surface area of a sphere, which is 4 pi r squared times the magnitude of the electric field E, is equal to the charge inside the sphere Q divided by the permittivity of free space epsilon naught. However, we don't have a charge in smaller sphere, so the electric field is 0. If a closed surface has no net charge enclosed by it, then the net flux through it will be 0. Now let's see what happens with the larger sphere. The symmetry arguments hold for this sphere as well. But if we take a look at the equation, we will notice that Q is not 0, because there is a charge inside that sphere. So the magnitude of the electric field will be equal to the charge enclosed divided by 4 pi epsilon naught r2 squared. If we draw a graph with the distance on the x-axis and the magnitude of the electric field on the y-axis, we can notice the following. Up to the point r, which is the radius of our initial sphere, we have no electric field, but then it reaches its maximum value and decreases as the distance increases. The second type of symmetry is cylindrical symmetry. Let's say we have an infinite line of positive charge with uniform linear charge density lambda, and we want to figure out what the electric field is at some point above the line at distance r. Here we will choose a cylinder as a Gaussian surface with a center along the line of charge. We don't have an electric field through the end caps. The electric field will be pointing out through the walls of the cylinder. Also, we have symmetry here, which allows us to use the Gauss's law in order to calculate the electric field. We can calculate the flux using the same equation that we used previously. But now we need to find the surface area around the cylinder, including the wall, without the end caps. For that purpose, we need to cut the cylinder along its length, and we will find out that the area is equal to 2 pi RL. So 2 pi RL times E is equal to the charge enclosed divided by epsilon naught. The charge density lambda is the total charge Q per length L, so the charge enclosed is equal to lambda L. So 2 pi RLE is equal to lambda L divided by epsilon naught. The electric field is equal to lambda L divided by 2 pi RL epsilon naught. L cancels out, so the electric field is equal to lambda divided by 2 pi R epsilon naught. The last type of symmetry is planar symmetry. In this example, we have a flat, infinite large horizontal plate. We will bring a charge onto this plate with a uniform charge density sigma. Sigma is actually an amount of charge per area and is expressed in coulombs per square meter. Now we want to calculate the electric field in the surrounding area of this plate, let's say at a distance d. In this case, we are going to choose a cylinder again as a Gaussian surface. The cylinder intersects the plate, and in that intersection we have a charge enclosed. In order to be able to calculate the electric field, we need to meet three conditions. First, the cylinder end caps with an area A must be parallel to the plate. Second, the walls of the cylinder must be perpendicular to the plate. Third, the distance from the plate to the end caps D must be the same above and below the plate. Now that we met the symmetry requirements, we can calculate the electric field using the Gauss's law. We are not going to have any horizontal components of the electric field, only vertical coming out of the two end caps. Sigma is equal to the charge divided by the surface, and from this equation we can see that the charge Q is equal to sigma times the area. The flux from the wall of the cylinder is equal to 0, so the total flux consists of two components, the flux through the top cap plus the flux through the bottom cap of the cylinder. This is equal to Q enclosed divided by epsilon naught, or sigma A divided by epsilon naught. But also, the flux through the top and the flux through the bottom can be expressed as EA, so the total flux is equal to 2EA. Finally, the electric field is equal to sigma divided by 2 epsilon naught. If the plate is positively charged, the electric field would be pointing outward, and if it is negatively charged, the electric field will be pointing inwards. If we draw a graph with the distance d on the x-axis and the electric field on the y-axis, we can notice that the electric field has a constant value of sigma over 2 epsilon naught, and it doesn't depend on the distance from the plane. Now let's take a look at another more complex situation of two infinitely large parallel plates. The first plate has a surface charge density plus sigma, and the plate below has a surface charge density minus sigma. The distance between them is d, so what is the electric field anywhere in the space? The positively charged plate has an electric field pointing away from the plate, equal to sigma divided by 2 epsilon naught. It doesn't depend on the distance from the plate, so it continues below. The negatively charged plate has an electric field pointing towards the plate, also equal to sigma divided by 2 epsilon naught. In order to calculate the total electric field, we are going to use the superposition principle by adding vectors. The vectors that are in the opposite direction cancel out, so the electric field there is 0. The vectors between the plates are in the same direction, so the electric field is sigma divided by epsilon naught. Here's how the electric field lines would look like. They will be pointing away from the positively charged plate and towards the negatively charged plate, and the electric field outside will be 0. Okay, so that would be all for Gauss's law. I hope this video was helpful and you learned something new. Don't forget to subscribe, and for more tutorials visit my website howtomechatronics.com.
Hi, and welcome. Today I'm going to talk a little about Gauss's law. Okay, so what is Gauss's law? What does it tell us? Well,
electrostatic potential due to a point charge. Vishal is climbing up a small hill. He is carrying his belongings in a sledge that he pulls up along with him as he is climbing. But as he reaches the top of the hill, the rope tied to the sledge gives way and the sledge comes hurtling down the hill. Now, why did this happen? While Vishal was climbing up the hill, both the sledge and he were working against the gravitational force. This energy was stored in them in the form of potential energy. When the rope gave way, this potential energy was converted into kinetic energy, resulting in the downhill motion of the sledge. Now, what would happen to a charge if it acts against Coulomb's force? Will it also gain some energy? Let us find out more about it through this animation. Look at this energy field in the XY plane. Let us place a positive charge plus Q at point O on this energy field. Look what happens. Observe that the energy around point O increases, and so the energy field gets distorted. Now, let's try to move a small positive test charge Q0 from infinity to the charge Q. And remember, let's apply just enough force to move the test charge without accelerating it. The electric field at infinity can be considered to be zero. It is very clear that a considerable amount of work has to be done to move the test charge against the electrostatic force of repulsion provided by the charge Q. This work done is stored in the test charge in the form of potential energy. This stored energy is called the electrostatic potential energy. So, electrostatic potential energy of a charge at a point in an electric field is the amount of work done by an external force in moving the charge from infinity to that point without accelerating the charge. Observe that whichever path we take to move the charge from infinity to the point O, we consider only the vertical distance from point O to the point charge to determine the electrostatic potential energy at that point. This means that the electrostatic potential energy will be the same along all the paths to a particular point. So, we can say that the electrostatic potential energy of a point charge is independent of the path taken by the point charge. It depends only on the initial and the final position of the point charge. Now, let us find out the amount of work done in moving a point charge in an electric field. Let us take a small section of the electric field E produced by the charge Q to understand the concept better. As you can see, in this small section, the electric field is non-uniform. We will move the positive test charge Q0 from point A to point B against the electric field of repulsion produced by the charge Q. We can choose any path. Let us take the path indicated by the green line. At the distance r from Q, the electrostatic force F on the test charge is equal to the product of Q0 and the electric field E. So, for a small displacement dr of the charge against the electric field, the amount of work done dW is equal to minus F dot dr or minus Q0E dot dr. If the angle between the direction of the electric field E and the direction of the displacement of the charge dr is theta, dW is equal to minus Q0E cos theta dr. Clearly, to move the charge from A to B, the work done WAB is equal to minus Q0 line integral A to B E dot dr. By definition, this is the potential energy difference between the point A and the point B for the test charge. So, when the charge is brought from infinity to any point R, the work done becomes equal to the absolute potential energy at that point. See, this expression also shows that electrostatic potential energy is independent of the path. It is clear from the expression that the potential energy of a charge in an electric field is dependent on the charge value. But if we take the potential energy per unit charge, the expression becomes independent of the charge value. This value of potential energy per unit charge is called electric potential and is denoted by V. So, electrostatic potential is the characteristic of an electric field only. For every point on the electric field, we will get a unique potential value. Therefore, electrostatic potential of a point in an electric field can be defined as the work done to move a unit positive charge from infinity to that point without accelerating the charge. Let us now find out the potential at a point due to a point charge q. We see that the electric field is directed radially outward from the point q. Let's take a unit positive charge from infinity to a point r at distance r along the radial direction. So, the angle between the small displacement dr along the path and the electric field is 0. We have already seen that the work done to move a unit positive charge from infinity to a point at a distance r in the electric field is equal to minus line integral infinity to r E dot dr. But E is equal to q by 4 pi epsilon 0 r square into unit vector r. So, the work done in this case can be calculated as shown. According to the definition of electrostatic potential, this is the electrostatic potential at point r due to charge q. So, the potential V at any point due to a point charge q is equal to q by 4 pi epsilon 0 r. Clearly, electrostatic potential is inversely proportional to the distance. So, if we draw a potential versus distance plot, it will be a hyperbolic curve. Let's recapitulate what you have just learned in this animation.
Introduction. Prince and his father are standing at the window side and viewing outside. It is a rainy weather. Suddenly, lightning occurs and falls down. Prince observed that the tree on the road catches fire due to lightning. He asked his father that why tree catches fire and the car remains safe on the road. His father replied him that it's due to electrostatic shielding. When lightning falls on the car, then all the charge flows through the other surface of the car and then grounded. But in case of the tree, it does not happen. Students, you must be more curious to know and learn this fact and topics. So let's study more about this in the chapter Electrostatic Potential and Capacitance. Objectives. At the end of this lesson, you'll be able to define electrostatic potential, calculate potential due to a point charge, system of charges, and an electric dipole. Define principle of superposition for electric potential. Define equipotential surface. Define potential energy. Calculate potential energy of a system of charges and electrical dipole. Know electrostatics of conductors. Explain electrostatic shielding. Electrostatic potential. Electric potential of an electric field at a given point is defined as the amount of work done in bringing a unit positive charge from infinity to that point. Electric potential is measured in volt. If 1 joule work is done in moving plus 1 coulomb charge from infinity to a point in an electric field, then the potential at that point is 1 volt. The potential difference between 2 points A and B is given by VAB equals WBA upon Q naught. The potential difference between 2 points in an electric field is equal to the amount of work done in moving a unit positive charge from lower to higher potential point. Potential due to a point charge. A point charge plus Q is situated at a point O in space. This charge creates its own electric field E around itself. We have to calculate the potential of this electric field at point A. We consider 2 very close points, P and Q, on the line OA. The total work done in moving plus 1 coulomb charge from infinity to point R is given by W is equal to 1 upon 4 pi epsilon naught multiplied by Q upon R. This amount of work is the potential of the electric field created by the point charge plus Q at a distance R from Q. We can show in the graph that as R increases, the potential falls down hyperbolically. If point A is at higher potential than point B, then the potential difference between the 2 points is given by VAB equals VA minus VB. Put the values of VA and VB, we get VAB is equal to Q by 4 pi epsilon naught multiplied by 1 upon A minus 1 upon B. Principle of superposition for electric potential. Let us consider 2-point charges plus Q1 and plus Q2. Take any 2 points A and B in the combined electrostatic field of 2 charges Q1 and Q2. Choose a curve L between A and B. We know that VB minus VA is equal to minus integration from A to B of E vector dot dl vector. But according to principle of superposition of electric fields, E vector is equal to E1 vector plus E2 vector. Therefore, VB minus VA is equal to minus integration from A to B of E1 vector plus E2 vector dot dl vector. So, electrostatic potential differences are additive. If A is taken to infinity, then V is equal to sum of minus integration from infinity to B of E1 vector dot dl vector and minus integration from infinity to B of E2 vector dot dl vector. So, the electrostatic potential at B is the scalar sum of potential at B due to charge Q1 alone and potential at B due to charge Q2 alone. This result is applicable for any number of charges. Potential due to an electric dipole. We consider a dipole with 2 charges, plus Q and minus q separated by a distance 2L from each other. We calculate the potential of the field due to this dipole at different points. Potential at an end-on point. Consider an axial point P at a distance r from center O of dipole on the side of plus q. The potential at P due to plus q is given by V positive equals 1 upon 4 pi epsilon naught multiplied by q upon r minus 1. The potential at P due to minus q is given by V negative is equal to 1 upon 4 pi epsilon naught multiplied by minus q upon r plus 1. The total potential at P is obtained by having direct addition of the two and is given by VE is equal to 1 upon 4 pi epsilon naught multiplied by P upon r square. This shows that the potential along the axis of dipole falls inversely with the square of distance. Potential at broadside point due to an electric dipole. Consider a point P on the equatorial line at a distance r from the center of dipole. The potential at P due to plus q is given by V positive equals 1 upon 4 pi epsilon naught multiplied by q upon under root r square plus L square. The potential at P due to minus q is given by V negative equals 1 upon 4 pi epsilon naught multiplied by minus q upon under root r square plus L square. The total potential at P is obtained by having direct addition of the two and is given by VB equals 0. This shows that the potential at any broadside on point is 0. Potential in plane of an electric dipole. Consider a point P on the plane of dipole at a distance r from center O of dipole, and PO makes an angle theta with the axis of dipole AB. The distances of P from A and B are R1 and R2 respectively. The total potential at P is given by V equals Q upon 4 pi epsilon naught multiplied by R1 minus R2 upon R1 R2, which is equal to 1 upon 4 pi epsilon naught multiplied by P cos theta upon R square. This is a generalized expression for representing the potential of a field of short dipole at any point on the plane of the dipole. Potential due to a system of charges. Consider the point charges Q1, Q2, Q3, and so on till Qn at distances R1, R2, R3, and so on till Rn respectively from a point of observation P. The resultant potential at P due to all the charges is the algebraic sum of the potentials at P due to individual charges. This is because electric potential is a scalar quantity. The resultant potential at P is given by V as V1 plus V2 plus V3 and so on till Vn. Equipotential surfaces. An equipotential surface is the locus of points at which the potential due to a charge distribution is same. No work is done in moving a charge from one point to another along an equipotential surface. In a point charge for a given radius, electric potential is same, and the equipotential surfaces are spherical surfaces centered on the charge. Electric field lines created by any system of charges are always perpendicular to the associated equipotentials. Example on equipotential surfaces. Let's take an example on equipotential surfaces. An infinite thin plane sheet of charge density 10 raised to the power minus 8 coulomb per meter square is held in air. How far apart are two equipotential surfaces whose potentials differ by 5 volt. Let's see the solution. We know that electric field intensity E is equal to sigma upon 2 epsilon naught. Since E does not depend upon the distance from the plane sheet, therefore E is constant for the given problem. If delta x meter is the separation between two equipotential surfaces which differ in potential by delta V, then E is equal to delta V upon delta x. We evaluate the value of delta x as 2 epsilon naught delta V divided by sigma. By putting the values in the equation and evaluating, we get the value of delta x is equal to 8.85 millimeter. Potential energy. The potential energy of a charge Q present at a point in an electric field is equal to Q times the potential of the field at that point. U is equal to QV. The unit of potential energy is Joule. Bringing of any charge Q from infinity to a point A in an electric field E will require a work WA to be done on the charge, which is stored in the charge Q as its potential energy. UA is equal to QVA. The electric potential energy of a system of stationary charges is the work that has to be done in bringing these charges from infinity to the points near each other to form the system. Potential energy of a system of charges. The potential energy of a system of point charges is the work required to assemble this system of charges by bringing them in from an infinite distance. Potential energy of the system of two-point charges. The electrostatic potential energy of the system of two-point charges is given by U as 1 upon 4 pi epsilon naught multiplied by Q1 Q2 upon R12, where Q1 and Q2 are the electric charges of the 2 points. R12 is their separation distance. Potential energy belongs to the system as a whole and not to any individual charges. Note that the electric potential energy is the product of charge and electric potential. Potential energy of the system of 3-point charges. The potential energy of the system of 3-point charges is the energy required to assemble the system of 3-point charges from an initial situation in which 3 charges are infinitely far apart. The procedure for calculating this electric potential energy is to calculate the potential energy for every pair of charges separately and to add the results algebraically. The electrostatic potential energy of the system of 3-point charges is given by U is equal to 1 upon 4 pi epsilon naught multiplied by Q1 Q2 upon R12 plus Q2 Q3 upon R23 plus Q1 Q3 upon R13, where Q1 Q2 and Q3 are the electric charges of the 3 points, and R12, R13 and R23 are their separation distances. Potential energy of an electric dipole in an external field. Consider an electric dipole of dipole moment P is placed in a uniform electric field E. The dipole experiences 2 equal and opposite forces plus QE and minus QE at its ends forming a couple. Magnitude of the torque on the dipole is equal to magnitude of the force into arm of the couple. Tau is equal to QE into 2L sine theta, which is equal to PE sine theta. Work done in rotating the dipole through a small angle d theta is equal to tau d theta, which is equal to Pe sin theta d theta. Total work done in rotating the dipole from an initial orientation theta naught to the final orientation theta is W equals to minus Pe cos theta minus cos theta naught. If the initial orientation theta naught is equal to 90 degrees, then W is equal to minus Pe cos theta. This work is stored as potential energy. Thus, potential energy of the dipole is U as minus Pe cos theta, which can be written as minus P dot E. Electrostatics of conductors. A conductor is said to be in electrostatic equilibrium if there is no net movement of charge within and on the surface of the conductor. The electric field is zero at all points in a conductor. The electric field just outside the surface of a charged conductor is perpendicular to the surface. Excess charges on an isolated conductor in an electrostatic condition reside entirely on its surface. Excess charges on an irregularly shaped conductor tend to accumulate at locations where the curvature of the surface is greatest. The electric potential is constant everywhere inside a conductor and equal to its value at the surface. Electrostatic shielding. The placing of a grounded metal screen or enclosure around a device to prevent electric fields from interacting is known as electrostatic shielding. It is the best way to protect some area in vacuum from the influence of external electric field. Electric field is zero inside a conductor of any shape in electrostatic shielding. If a conductor A kept at zero potential surrounds conductor B, then B is said to be electrically shielded by A from other electric systems. For example, in a thunderstorm accompanied by lightning, it is safer to be inside a bus or car rather than near a tree or open ground. Did you know? Volta had already created the electrophores to create static electric charges and discovered methane. The volt was officially established in 1881 as an electrical potential of 1 joule per coulomb of charge. It is used around the world. The electric potential decreases in the direction of field and increases against the direction of electric field. Equipotential surfaces and electric lines of force constitute a mutually perpendicular network. Summary. Let us summarize what we have learned. The potential difference between 2 points in an electric field is equal to the amount of work done in moving a unit positive charge from lower to higher potential points. Electric potential of an electric field at a given point is defined as the amount of work done in bringing a unit positive charge from infinity to that point. Potential along the axis of dipole falls inversely with the square of distance. An equipotential surface is the locus of points at which the potential due to a charge distribution is the same. The electric potential energy of a system of stationary charges is the work that has to be done in bringing these charges from infinity to the points near each other to form the system. A conductor is said to be in electrostatic equilibrium if there is no net movement of charge within and on the surface of the conductor. The placing of a grounded metal screen or enclosure around a device to prevent electric fields from interacting is known as electrostatic shielding.
When you're walking on a street, let's say somebody comes to you and say, hey, electric potential at some point in space, let's call it pointer C, is 20 volt. What is the meaning of that statement? What would it mean? So by the end of the video, you'll be able to explain this statement in very simple terms to someone. To begin with, we are familiar with this word potential energy. And we've learned of potential energy when it comes to gravity. So let's start there. Say we held a 5 kilogram bowling ball in our hand, and I know bowling balls are a little larger than this, but imagine we held it at some distance from the ground, then we say that it has potential energy. Why do we say that? We say that because if I let go of that ball, then as it falls down, it's going to speed up, and it's going to gain kinetic energy. And we could ask, where did that kinetic energy come from? For example, let's say at this point we calculate and we figure out that the kinetic energy at this point is, I don't know, maybe 55 joules. And we don't have to worry about how to calculate that. Let's just take some random number. We could ask, hey, where did this 55 joules come from? Where was this before? Because energy can neither be created nor destroyed. And so we say, this 55 joules was already stored in the ball even before releasing it. And that energy is what we call potential energy. And so according to our example, this ball now has a potential energy, and the symbol we use for potential energy is usually U. And we say the potential energy of this ball is that same 55 joules. Okay? Now here's my question to you. My question is, a 5 kilogram ball held at this point has 55 joules. How much potential energy a 1 kilogram ball held at this same point have? Can you pause the video and think about this? All right, hopefully you've tried. So you might know that less mass means less potential energy. In fact, if I have only 1 kilogram, 1/5 of the mass, then even the potential energy would be just 1/5. And so 1/5 of 55 would be just 11 joules. All right? And so you know what I can do now? I can get rid of this ball, and I could say at this point, and I could put a indicator, I can label that point and say, let's call it point A, and I could say at this point, the potential energy is 11 joules per kilogram. That's how we can write. And what this means is if I were to keep 1 kilogram over here, it would have 11 joules of potential energy. And this number, how much potential energy you get per kilogram, is what we call potential. And we will write A over here because this is potential at point A and this is potential energy at point A. So do you see the difference between them? Potential is just potential energy that 1 kilogram would have. It's an indicator. Just like how when you go to grocery stores, you have indicators over there which says, hey, 100 rupees per kilogram. This means if you buy 1 kilogram, you pay 100 rupees. But it could also mean that if you buy 3 kilograms, you have to pay 300 rupees, and so on and so forth. Similarly, it's an indicator which says, hey, if you keep 1 kilogram, it would have 11 joules of potential energy. But you could keep 10 kilograms over here, and it would have 110 joules of potential energy. So that's what gravitational potential is. So this is gravitational potential. Similarly, we can now define electric potential. So let me consider an electric potential case. So let's say we have something very similar. We have now a bowling ball which is charged because we want electricity. And let's say it has 20 coulombs of charge, a lot of charge. And let's say we have another huge charge which is negatively charged over here, somewhere down over here. And so now we have a situation which is very similar to that of gravity. If I were to let go of my hand, we know that that thing is going to get attracted towards this. And let's assume this is fixed, then for simplicity, okay? And then it's going to get attracted.
Yeah, we will close at this because he has got some doctor's appointment. Manish has got some doctor's appointment. We will meet again the next.